Hopefully that previous video kind of gave you a sense for what are differentials. But the basic idea here, guys, is differentials are really small changes in x and really small changes in y. And what we can do is use this guy dy to try to approximate the actual change in a function. So dy is the change in a tangent line, where delta y is the change in the actual function. So how do we use it? What do the problems look like that you guys are going to start seeing? So here's an example. So let's find delta y and dy at x equals 2 using a small change, right? Our differential in terms of the x is 0.01 for the function x cubed. So I've gone ahead and drawn it. And just to kind of be over the top here, I'm going to call this, here's my change in x. dx is 0.01. So we're going to go out to 2.01. The idea here, right, so here's our tangent line. The tangent line slowly gets away from the actual function at 2.01. But the idea is we can use this blue line to try to approximate what's actually happening on the function at 2.01. Right? 2.01 of the function is way up here. Right, so here's f of 2 plus 0.01. And here's f of 2. So, delta y, if you want to think about it this way, delta y would be this distance between f of 2 and f of 2 plus 0.01 or f of 2.01. dy, keeping in mind, so there's your change in x. dy is the change on the tangent line. So you can see it'll get us close to the actual y value, but we still have this little bit of a gap in between, right? So, we saw in the video, at the very least, what we can kind of pull up with is, formula-wise, dy equaled f prime of x times dx. And what we did there, again, is basically we took the two different names, right? dy dx is another name for f prime of x. We just moved the dx to the other side. So really what we're looking for here, guys, is what is the slight change in y associated with this function when the slight change in x is 0.01? What is the slight change in y? That's what dy is. So first things first, let's get f prime of x. So f prime of x would be 3x squared times dx. And we know that x that we're of interest here is 2, and the dx that we were given is 0.01. So that would be 3 times 4, 12 times 0.01 gives me 0.12. So my change in y is 0.12. Now, is that how much the function actually changed? Well, no, the function should have actually changed a little bit more. And to find delta y, it's really not too complicated of a process, especially since we have the function, right? But this is just to kind of get the ball rolling. Hopefully you guys see it. All we have to do, guys, is plug in f of 2.01 and subtract f of 2. So really, if we just got to find the distance between those 2 points. So plug 2.01 into the function, and it should kick back 8.1206, and f of 2 cubed is 8. If we do that, the actual change in the function was 0.1206. So our delta y should have been, right, the actual change in the function was 0.1206. We approximated it using the differential at 0.12. So our differential was very, very close. Because we didn't take a huge step with x, we're not that far off in terms of our y values. Another application, you could use it to approximate square roots. Right? Maybe back in the day, that's what some folks did. So go ahead and pull a function out of this, right? If we're going to use differentials, that means we need, if we're going to use dy, we need some kind of function, and we need some kind of change in x, right? We need some function. Right? And our goal, again, dy is is what we're using to approximate delta y, right? So this is a slight change, square root of 26, right? So we see our function here is square root of x. We can go ahead and do this. We know we're going to need to use a differential, a derivative. So that would be what? 1/2 x to the negative 1/2. And if you want to think about it, that's 1 over 2 root x. So there's our derivative. We're going to end up having to use that to approximate. Right? So we've got this square root function. We're basically going to come to 20. We're going to use something really, really close. Well, what's really, really close to 25? 25, is incredibly close to 26. So why don't we use x equals 25 to do our approximation, which now gives us a delta x to work with. Well, what was the change in x from 25 to 26? That'd be a delta x of 1, or a dx of 1. So now all of a sudden, we'd like to, again, f of 26 is actually going to be a little bit lower. So here's f of 25. F of 26 is actually a little bit lower than what our differential, our derivative, is going to try to calculate for us. But it should be pretty close. All right. So let's plug in what we know. So our dy equals f prime of x, 1 over 2 root x times dx. Now plug in the numbers we know. We have 1. The x we're going to use to approximate is 25. And the delta x we have is 1. We changed by 1 value. So that would be 1 over 2 times 5. So that's 1/10. So our change in y is 1/10. And the idea, our end goal is to try to approximate the square root of 26. Well, the idea here, f of 26, so we're not quite done with this problem, would be f of 25 plus, right? If we want to get up to f of 26, we'd have to add that delta y. Well, the problem is we don't know delta y. But we did have a really, really nice approximation of delta y, dy. So what we can do, instead of getting the exact value for f of 26, we can say the square root of 26 is approximately f of 25 plus dy. So the idea here, we're going to use this value to approximate that lower value. So for us, f of 25, square root of 25 is 5. And the differential that we're interested in is 0.1. So the square root of 26 is approximately 5.1. Check in your calculator. I bet we got really close. So guys, it's at this point that I would say if you wanted to, take a look in the book. It's going to be section 3.9. There should be enough up in the front where you guys could grab those and kind of pick through some of the practice problems in section 3.9. And just in case maybe you've lost that sheet, there you go. So we're in section 3.9. Grab a book from the front of the room, and the problems you guys, if you want to take a look at it, we can at least start in section 3.9. The book's actually going to suggest, as I'm looking at it, that you guys do some problems that we're not quite ready for, but we will. So what I would suggest, if you guys will, go take a look at problems 7 through 10, and then 11 through 19. 7 through 10, you're going to be asked to evaluate and compare delta y and dy, kind of like we did in the first example in this video. And the next one is just going to ask you to find the differential. In other words, they want you to find dy, and they're going to give you a function. All right? Don't overthink this one. Really, all you have to do to find dy, you just need to find the derivative of the given function. So you might have to use your power rules, product rules, chain rules. You do that derivative, and then throw a dx on the end. That's the differential dy.